Thank you. So yeah, Antarctica, the awakening giant. Why do we call it that? Antarctica stores 2/3 of all freshwater on Earth. So that's more freshwater than you can find in all rivers, lakes, groundwater, reservoirs everywhere on Earth. And that's locked up as ice in Antarctica. And if that were all to melt, it would raise global sea levels by 58 meters. Now, that's not what we're concerned about in sort of contemporary situations today. And we are fortunate that Antarctica is a dry, windy, and cold continent. But this is changing. It's warming and it's becoming wetter. So the awakening giant, where do we see signs where things are changing in terms of the balance between ice gained by snowfall and the losses due to melt and icebergs breaking off? We can see that in the West Antarctic side of the ice sheet, where you can see the big red circles, these are places where we've known for a while that there's been a very vigorous contact of the ice with the ocean and an intense interaction. So this is Thwaites Glacier in West Antarctica, which I will talk a little bit about in later slides. We can also start to see some of these signals in the Australian Antarctic territory at Totten and Denman. And if we compare this east versus west, we can see that actually the numbers in east are sort of starting to look a bit comparable. And these are regions that have seen far less attention than glaciers such as Thwaites Glacier in West Antarctica, which has been referred to in some news outlets as the Doomsday Glacier. I think it goes back to an article by Rolling Stone magazine about 10 years ago, and it's sort of stuck since. It's not what we call it. But the reason that it's been sort of coined the Doomsday Glacier is that this glacier in West Antarctica has been known for over 10 years to have a precarious setting, a setting in which the interaction with the ocean can become unstable, and retreat of the glacier down this retrograde slope that you can see becomes deeper and deeper, that can become a self-reinforcing mechanism. So here we've got a simulation by Chen Zhao here in ACEAS, who's been studying all of the drainage basins in Antarctica and found Thwaites Glacier, like many other studies, to be a particularly concerning location in terms of generating retreat. And perhaps what is the most concerning here is that we know the glacier was pinned at this pinning point in the 1940s, and today it's pinned on this pinning point, and it's retreated about 60 kilometers so far over less than 100 years. And if this glacier are to retreat another 40, so less than it's actually been observed to retreat, we hit that tipping point where the retreat becomes self-reinforcing, and there's really nothing we can do to avoid that. So this is what makes this glacier a precarious glacier. But there is good news in this, because it's not in all of our simulations that we necessarily get this runaway effect. It really depends on the nature of how we parameterize the friction at the underside of the glacier. And that's something that makes my life very difficult as a glaciologist, because we're trying to figure out what that friction is. This is not something we can easily measure from a satellite. It requires detailed observations about the topography and the nature of the sediment or the rock underneath the glacier. So if we have a relatively strong parameterization, we don't get that runaway effect. And the glacier sort of remains pinned at the current pinning point. So that is definitely something to celebrate. But we don't know whether that's which of these two situations we are really in today, whether we are in an unstable or approaching an unstable situation, or if we now have a stable pinning point. So that's why scientists such as myself go and venture onto the ice sheet. It's really important that we can do these types of in situ measurements. In this case, drilling through over 1 kilometer of ice in order to take samples and study the underside of these glaciers that are contributing to sea level rise. All right, okay, so So we talked about Thwaites Glacier here. That retreat that I mentioned, the 60 kilometers retreat, that equates into an area that the glacier used to be pinned on, that's been lost, an area that used to provide friction to hold back the ice. That aerial loss is about 1,100 square kilometers. For Pine Island Glacier and other West Antarctic Glacier that's undergone quite significant retreat, it's also about 1,000 square meters of friction that's been lost. For the eastern side, for the glaciers in the Australian territory, these numbers are lower, but they're still on the order of 500, 600 square kilometers, areas that we can see that has been lost, areas that are starting to show signs of retreat, and retreat that we are worried about, because sometimes when we get a retreat from a pinning point, we can get an imbalance in terms of the ice gained and the ice lost, and that's why ice sheets can undergo these continuous retreat episodes where we lose all the ice in a drainage basin. So if we go to the latest report by the Intergovernmental Panel on Climate Change, you can see graphs like this about sea level rise. Until 2100, we are sort of on track to approach perhaps close to 1 meter of sea level rise, maybe little bit less with the current rate of change. If we manage to move into a better scenario or more green technologies and solar energy and have less climate change, we can perhaps end up in a situation where sea level rise is kept under 1 meter. But even on today's trajectory, we're talking about sea level rise on several meters by 2300. And the 2300 is because the reaction of the ice sheet to the heat contained in the ocean and the atmosphere is quite slow. But the flip side of that coin is that once things start, it's very difficult to stop. Okay, so the red dashed line that you can also see in IPCC sea level projection is a scenario that we don't think is particularly realistic at this point in time. So we may not need to really worry about those very extreme rates. But even without that instability here, we can see that we are approaching several meters of sea level rise over the coming centuries. Now let's have a look at sea level rise as it's been studied by records since 1995 until present day. And here, perhaps the most important thing is to just appreciate that this is not a straight line. This is a graph where you can see a curvature on it, right? So if you take the rate of change in the early 19s, that was about 2 millimeters per year. If you take the rate of change closer to present day, it's about double that at 4.5 millimeters per year. So there's definitely growing contributions to sea level rise. And these growing contributions are Antarctic and ice in Greenland and glaciers that are melting faster than they did 30 years ago. So why is that important? Well, it's important because we don't have to only worry about the magnitude of sea level rise in terms of the high-end scenario. Is it going to be 1 meters or 1.1 meters? Actually, with 0.2 meters of observed sea level rise over the last 100 years, that in itself has made a 1 in a 100-year event into a 1 in 10-year event. Over the next 50 years, we're pretty certain that we're going to get another 0.2 meters of sea level rise with the rate at which we're observing it today. And that will turn that same event into an annual event. So in Australia, we have got 370,000 residential properties and 120,000 industrial properties that could become uninsurable, according to AON. So there's hundreds of billions of infrastructure that's exposed to this risk. So let me just try and explain that just quickly with a little graphic. So here we can see a schematic representation of the situation in 1990. We've got a mean sea level rise with a high tide and a low tide fluctuating around the mean. And right at the end of that limb, you can see the very extreme situation of a high tide event. If we raise sea level by 0.1 meters, which is what we've seen since 1990, you can see that we get a new extreme in that end of the spectrum. And what used to be the event that happened twice with n equals 2 now becomes n equals 6. And that's simply just due to the statistical distribution of these numbers. So that's why 0.2 meters or 0.1 meters of sea level rise really has a huge effect on the extreme flooding that tidal inundation can cause. So we have to worry about sea level rise, not just in terms of whether it's going to be 1 meters or 1.5 meters, but 0.1 meters, 0.2 meters are really important in a contemporary situation today. Thank you.